Hey, it's Dr. J. I'm back with part 2 of the section 3.5 on transformations of functions. So we've already talked about the 4 different types of transformations. Instead of just listing them all out, I'm just going to go ahead and start with an example. Before I start graphing, we're going to start with just examples, reviewing the different types of transformations. So let's start with my favorite of all is the graph of the quadratic. Suppose y equals x squared. That's what our mother function is stretched vertically by a factor of 4, reflected across, or about, we can also say across, there's only one C in across, that's why I like to say about. Across, about, over, those all mean the same thing. The x-axis, then translated, that's a fancy way of saying shifted, left 5 units, and up 3 units. The equation of the new graph is what? Now, unless I specify a name like F or G, you can just start your equation with y unless told otherwise. So maybe later in this lecture, I will say the function should be called f, or the function should be called g, or something like that. But this is just the generic name for an equation of a function, y equals. So I'll give you that for free. And now you want to go through all of the different transformations. So we're going to start with this function, x squared. That's our template. That's our mother. Remove the x, and then make a blank set of parentheses. That's your mother function. That's your template. Okay? And let's go through all the different transformations. There's 4 different types. So stretched, factor of 4. So that means multiply by 4 outside of the parentheses. Okay. Reflected about or across the x-axis. Let me draw some arrows here. Factor of 4 goes here. Reflected about the x-axis. That's going to go out in front. -1. You multiply by -1. Okay, that's because it's the x-axis. So you multiply outside. If it said y-axis, then I would multiply inside. Okay. And then we have shifted left 5 units. Remember, left is positive. It's opposite. That one takes a little getting used to because most people think of left as going negative, which, by the way, negative is still left when you're graphing, But when you're transforming, and I say transform it to the left, you're going to add 5. And at some point in this lesson, I might illustrate why that's true. And then finally, up 3 units, up and down, that goes outside. And so there you go. I like to clean up my answer. We typically get rid of the dots, and we typically combine the -1 and the 4, and we just say -4. But that's all. We do not actually square this out. We do not distribute the -4. We do not combine the 5 and the 3. I almost screwed that one up. And so this is the new graph. It's transformed. Okay, so it's undergone a transformation. Later in this lesson, I'll actually draw a graph of this. I've got my board handy, and we will do all the transformations on the graphing board. If I start doing that now, this example will last another 10 minutes, and I'd like to give you some more examples. Okay. So there we go. That's what I often think of this as like building blocks, almost like Legos, and you're just sort of snapping together all the different parts. And you really just want to get used to which parts go in what place. So suppose y equals the square root of x is reflected about or across the y-axis. And shifted right 5 units. No, we already did that. 6 units. Need some variety. Okay, what is the new graph? What is the equation? Of the transformed function. Okay. So this one only has 2 transformations. We have reflected about the y-axis, and then we have shifted, or shifted means the same thing as translated, right 6 units. So we have 2 different transformations. There is no specification as to what the name of my function should be, so I can just call it y. That's sort of the generic name. If you want to give it a name, you probably can get away with that. You can call it f or g, but I'm only going to do that if the question tells me to do that. I don't even have to take a risk. All right, so here's your mother function. Some people call it the parent function. Some people just call it the basic, or some people call it the toolkit function. Those are all different names. I just like to say mother function. Remember, you're going to remove the x and put a blank set of parentheses. All right, this used to be your x. So now, when you reflect about the y-axis, you want to multiply the inside by -1. You don't really need the dot, but I'm going to do it anyway. That's the main thing you want to memorize. If it's x-axis, you multiply outside. If it's y-axis, you multiply inside. And if it's both, you do both. Okay, and then shifted right 6 units. Remember, right means x minus 6. And you can clean this up by distributing the negative. And so there you go. There's your answer. You don't have to distribute the negative. I would still mark it right if you didn't. But you should probably at least get rid of the dot. I mean, most people do. Yeah. You can even get rid of the 1. So I would also accept this. I don't know why I'm having such a hard time writing the letter Y. There we go. I would also accept that. Yeah, I mean, you do need to do some simplifying. It's because this is a math class, right? So, I would get rid of the 1, I would get rid of the dot, and you could write it this way, or you could write it this way. Personally, I'd probably write it this way. You know what? You could also write it this way. So there are lots of different answers. I like to put the positive first, and then the negative last. That's clean. Simple, yeah. Clean and simple. All right. I mean, not that this one's not clean, but whatever. So I have 3 different, answer key, 3 different answers that it will accept. Okay. One of the functions that we didn't get a chance to graph or even discuss in part 1 was the reciprocal function. Right, an equation for a function that is the shape of y equals 1 over x that has been shifted left 2 units and up 3 units. So this transformation only involves the shifts, left, right, up, and down. In this case, it's going to be left and up. So again, take your parent function, remove the x. So that used to be your x variable here. We don't have any reflections and we don't have any scalings. So we're just doing shiftings. So let's do left first. Left would be x plus 2. And then up would be outside. Don't put it up in here. Put it off to the side. Plus 3. I'm just going to write it again. This doesn't have any simplifying. I'm just writing the answer one more time so it's absolutely clear. I mean, it was probably clear back here. But I don't want you to take that 3 and put it down here. That's what I'm trying to prevent you from doing. So make sure that the plus 3 is off to the side. It's not in the numerator. It's not in the denominator. It's off to the side. Some people put it out in the front, but then that kind of confuses the whole concept of, left, right, up, down, front, back, center, things like that. So I just put it off to the right. You can remove the parentheses if you like. If you want to do some simplifying, you just want to make your answer look a little bit cleaner, you can drop the insurance policy. That's what I call parentheses. They're like an insurance policy. Okay. Sometimes the function has a name like f. This is what we call a generic function. I'm not being specific. It's a general function. So this is what we call a general or generic function. General or generic function. In other words, it's not specific. I'm not telling you which mother function this is. This is just a general function. So we're not actually going to use an actual mother function. We're just going to take this generic function, y equals, and we're going to apply the transformations, right 1 unit. So we're going to say x minus 1, because that's right. And then down 4 units, minus 4 on the outside. So this is not specific. This can be applied to any function. Okay. So when we have a general transformation, such as y equals f of x minus 1 minus 4. That's the one we just did. We can apply it to any function. I'll call it an MF, any MF. For example, and I'm not numbering this one because this is really just me talking to you a little bit before I do the next problem. For example, if I say f of x is the absolute value of x, well, then y is equal to, we take this transformation, we remove f, and replace with absolute value bars. So remove the letter f, remove it, and replace it with absolute value bars. And there you go. Usually we remove the parentheses as well for this type of function. Although if you keep the parentheses there, I'm not going to mark it wrong. It's still correct. So basically, f is just telling you some mother function. It could be any of the mother functions that we talked about. Let's try them all. I just got to, all right? Suppose it was x cubed. Well, I'll do 6 of them, the 6 that I want you to know. There are 8 total, but let's just do the 6 of them. All right. So remove f and replace with a cubic function. So my equation would be remove the f, replace with a cube. So don't keep the f here, get rid of it. And there you go. For cubics and quadratics, we like to keep the parentheses. Everybody else, that we pretty much get rid of the parentheses. Maybe I'll just do another one right here. If f of x is x squared, then I would remove f. So remove the letter f and replace with square function, quadratic. So that would be quadratic squared, and then keep everything else the same, x minus 1, and then minus 4. Yeah. So that's 3 of them. Let's do the other 3. Suppose f of x was the square root of x. So I would remove f and replace with the square root. So remove f, replace with the square root. Okay, and then we normally also get rid of the parentheses. It turns out that a square root symbol acts like a parenthesis already, so we don't actually need the extra parenthesis. If f of x was the cube root of x, remove f and replace with the cube root symbol. So we'd get y equals, remove the f, replace it with the cube root. I'm going to go ahead and get rid of the parentheses now. Okay. And I said I was going to go through all of them, so we might as well just go through all of them. I think there's one more, right? So we did absolute value, we did quadratic, we did cubic, we did square root, we did cube root. The last one would be reciprocal. So remove f and replace with 1 over blank. So that'll be 1 over, that becomes the f, then the blank, and then in the blank put whatever's, we call that the argument. The argument is x minus 1 and then minus 4. And I already said this a minute ago, you can remove the parentheses if you like. If you want to leave them, you certainly can. Okay. Let's do some graphing. I don't know if that was example 4 or not, but I'm going to call this example 5. So given f of x equals 2x cubed minus 7, okay, I'm going to ask you a few questions before we graph. Who is the parent is the parent function? Well, it's the cubic. This is the cubic. So the parent function is the cubic. Y equals x cubed. That's the parent function. Are there any reflections? Are there any reflections here? Is the outside being multiplied by a -1? No. Is the inside being multiplied by -1? No. So no. Or none. Yeah, there are no reflections. Are there any stretching or compressions? Is it being stretched or compressed? That would be right here. That would be a stretch, yes. Stretch by a factor of 2. And these are vertical, just in case it asks you, is it a vertical stretch? We call this a vertical stretch. It's like you took the y values and stretched them out. Are there any horizontal shifts? Is this graph being shifted horizontally? No, because the -7 is not inside parentheses. If the -7 were inside parentheses like that, then it would be yes. But since it's not, I'm not going to change the problem. The -7 is not in the parentheses, so no, none. And then finally, are there any vertical stretches? Vertical shifts. We already talked about the stretches. Vertical shifts. Yes. Down 7 units. That's what that -7 is. All right, so why am I doing all these questions before we do the problem? Well, there's 2 reasons. One, I'm going to put this on the homework and the quiz and the test and things. So yeah, that's always a good reason to do stuff, is so that you can get it right. But there's a much more important reason. And I know this is hard when you're a student because all you want to do is pass and get the points. But the more important reason is when you read a function for the rest of the semester, and if you continue in college mathematics for the rest of your college mathematical life, you always want to be asking these questions as you're reading the question. And when you get farther into this course, you won't even have to write this stuff down. You'll read the function and your brain will start asking these questions and you'll answer them mentally, and then you can move on and do the problem, right? So it's an analysis. You're not just reading, you're analytically reading, so that as you're reading, your brain is analyzing, what am I actually looking at here? What is the meaning of this? Okay, so now we're ready to graph. Okay? I know you've been waiting almost a half an hour to see me draw a graph now. I've been doing a lot of. So we've answered all those questions. So now we're going to start with the mother table, also known as the parent. Highly recommend memorizing these tables. I know this is an online class now, so you can have your notes and you can look at the tables, but if we were in person class, you would have to memorize these. I tell you what, if we were actually in person, I would make you only memorize the x's. That's what I'd tell you. I'd say, don't bother memorizing the y's, just memorize the x's. These are pretty easy to memorize, right? You probably already have them memorized. Then you plug these x's in to get the y's. All right. And ultimately, you'll probably just end up memorizing all of it. All right, so we're going to multiply all of the y's by 2. Yeah, because that's a vertical stretch by a factor of 2. Now, this drives some people crazy because it looks like you're multiplying the x by 2, doesn't it? I don't know about you, but I mean, I have eyes, and that looks like 2 times x, but it's actually not. Yeah, this is actually y. Look, y is x cubed. That's what an equal sign means, is. So even though it looks like you're multiplying x by 2, you're actually multiplying all the y's by 2. Okay? And then you're going to subtract 7 also from all of the y's. Okay? All right. And so now that's just the scratch work, really. I wouldn't recommend trying to do all that in your head. So even though I'm calling it scratch work, you should actually do it. And then now I'm going to go through the transformation. I'm going to get a new set of x's and y's. I like to use the name that was given in the problem. So if the problem tells me it's f, well, then I'm going to go ahead and call that f. Okay, the x's are going to stay the same. -2, -1, 0, 1, and 2. And the y's. Now be very careful. You must multiply first. If you subtract and then multiply, you'll get the wrong answer every single time. So -8 times 2, that's -16. -16 minus 7 is -23. That's going to be hard to fit on my graphing board. I probably won't graph it. -1 times 2 is -2, and then -7 is -9. Most common mistake here is you make a sign error. Pluses and minuses have been baffling college students since, they were first invented. 0 times 2, that's just 0. And then -7 just becomes -7. 1 times 2, that's 2. And then -7 is -5. 8 times 2 is 16. 16 minus 7 is 9. I'm probably, just for practical purposes, only going to graph these ones. Okay. Now keep your eye on the center. This is called the inflection point. So follow it through so you know where it goes. This is called the inflection point. You must plot that graph, that point first. Okay, so let's see. I've got my board here. One, two, -1, -2. Look at your y values. Decide where you want to place your points. 4, 5, 6, 7, 8, 9. So that's going to be -9. What else do I have? Actually, here. A +9. 1, 2, 3, 4, 5, 6, 7, 8. +9. All right, and then plot the inflection point first. So 0, -7. There's the inflection point. All right, now after you plot that point on your computer, you can just pick any other point. So let's do 2, 9. So there's 2 and 9. Now on a computer, you're done. All right, and I know the times are changing quickly. You know, there was a time where you would only plot 1 point and it would draw the graph, and then now it's 2, and someday it'll be 3. I'm going to do all of them. So 1 and -5, 1 and -5. So right about here. All right, let me put the negatives. Whatever. Okay, and then -1 and -9. So here's -1 and here's -9. Now clearly -23 doesn't fit. And I mentioned this before, if you get a point that doesn't fit, just ignore it. Now if all of your points don't fit, you made a mistake. But I mean, quite often you'll have 1 or 2 points that just don't fit on the graph. And there you go. There's your transformed function. Notice how it does a little bendy right here. That's called inflection. Yeah, some people do it with their voices. Inflection, right? That's that little bendy that you do with your voice sometimes, right? It's called a vocal inflection. In math, we just call it an inflection point. Yeah. It's to make sure that if you're drawing this on paper, that you don't draw a straight line. Because look, if you're not doing an inflection, you could very easily go and just blast right through like a straight line. And you won't even realize that it did that little woo, you know. Okay. Before I do the next example, let's just talk a little bit about the language. Maybe I should say, never mind. We're done with this. I was going to say, fine, I'll say it. You get a free answer here. Domain, -infinity to infinity. I think I mentioned this on the last one, but I'll tell it to you again. 2 of the graphs give you free answers. The cubic and the cube root both give you free answers, domain and range. You do not have to solve for them like we were doing in the past. You just take it. It's a free answer all day long. Yeah. All right, let's put this aside and talk a little bit about the vocabulary. I got to grab another pen. Okay, so let's talk vocabulary. Okay. So for the rest of the problems, we're going to have a shape that's going to have a term, a word that corresponds to that behavior. So on a quadratic or a absolute value, these points are called vertices, or vertex for singular. Okay? You must plot this point first. call that the vertex, or if you're speaking in plurality, you'll say the vertices. Maybe it's just my glasses. I don't know. How bad is it? It looks pretty bad. No, come back. Okay. For the cubic, and the cube root. So this is the cubic, this is the cube root. These are called inflection points. I'm just going to say PT for point. Again, plot this first. Make sure you plot the inflection point first. Man, it's really not behaving today, is it? There we go. That's clean. Okay. So again, quadratic, absolute value, cubic, cube root. I could write that down, but I think I already have several times. For a square root function, this is called a terminal point. A terminal is like at the airport, yeah, when you go to get on a plane. You might be getting on the plane, but somebody else is getting off the plane. So the word terminal means beginning and possibly the end. Or you can think of it philosophically, one end is simply another beginning, and we call that terminal. All right. Make sure you plot this first as well. I don't know why I'm writing this so many times. You're always going to plot these special points first. And it's good if you know what they're called, because then I'm going to be talking about them. So that's for the square root function. And then finally, for the reciprocal function, the reciprocal function looks like this. It has neither. It has no vertex, no inflection, and no terminals. Instead, it has asymptotes. Okay, those are called asymptotes. This is called the horizontal asymptote. I'm just going to abbreviate horiz. Asymptote. And this one's called the vert, or the vertical asymptote. All right. The way we graph asymptotes on a computer is you put a dot right here, and you're going to plot that first. You'll put a dot right where the two asymptotes intersect, and the computer will automatically draw two asymptotes, one of them vertically and one of them horizontally. If you were doing it on paper, you would just draw them one at a time, obviously. Okay. So again, really quickly, this is the quadratic, x squared. This is the absolute value. This is the cubic. This is the cubert. The cube root, that's supposed to be a 3. This is the square root. Notice that these look similar, but they're different. And then this one's the reciprocal 1 over x. Those are the 6 mother functions that are covered in this section. All right, so now that I've gotten that out there, let's do another example. And then when I'm using the lingo, you can keep that in mind. So example 6. F of x is negative 1/2 times the square root of x plus 4. All right, and then let's just run through all of the questions before graphing. Number 1, who's the parent or the mother function? The parent is y equals square root of x. That's the mother function or the parent function. Are there any reflections? Yeah, do you see a -1 anywhere? Yes. Yeah, this negative right here, that's an invisible -1. All right, this actually means -1 times 1/2. That's what that means. We don't typically write it that way. We just write it as -1/2, but it actually means -1 times 1/2. So what is it? Which axis is it? Reflect, about, or over, across. Which axis? It's on the outside. So that's the x-axis. Okay. Make a note, even though it's going over the x-axis, when we get to the graphing, we're actually going to multiply the y values. So just make that clear. Are there any stretches or compressions? Yes. That's this 1/2 right here. I think of the negative and the half as 2 separate transformations. So this is going to compress, also known as shrinking, vertically by a factor of 1/2. In other words, the graph is going to get shrunk half its size. All right. And then, are there any horizontal shifts? Is there anything going on inside? Yes. Shift left. I can almost hear the internet. I can hear your voice through the internet. Plus means left because it's on the inside. And then vertical shift. Is there any pluses or minuses outside of the radical? No, there are none. All right. I'm not sure. You're either going to answer no, or you're going to answer none, or there are none, or something to that effect. Okay. I'm not going to try and trick you. There'll be a clear answer of none for this one. All right, so those are all the questions that you want to ask. Again, at some point, you won't have to write all this stuff down. You'll just read the question, and we'll just talk about it as we're analyzing it. All right. So let's go ahead and do that. Let's take our mother table. Remember, this is a square root function. I think I have gone all the way to 16 in the past. I'm just going to stop at 9 for this one. Okay. So you can just combine these together. That's going to multiply by -1/2 all the y values. Do that first. Okay. And that's it. So that is both the compression and the reflection at the same time. If you want to do them separately, you can. You can compress them all, multiply them all by 1/2, and then in another step, reflect them all by multiplying by -1. I've never had anybody tell me that they want to do that because you could just combine them and do it all at the same time. Now, the tricky one is the +4. Because it's going horizontally left, you're going to add -4, or you could just subtract 4. I prefer to add -4. Make sure you don't do this. I'm telling you what not to do. And I'm watching. Somebody out there is going to do this. And I don't know what it is. Maybe I'm not making it clear, but or maybe it's just because I'm saying subtract, and therein lies the rub. When I say subtract, you say 4 take away, because that's the way you remember subtraction from when you were a little kid. Do not do that. That is awful. All right? It's much better to add a negative number than it is to try to subtract and get it wrong. I want you to get it right. All right, now it's going to go through the transformation. And this function has a name. Its parent gave it a name, f of x. All right, so let's just go through these. So I like to just do all the x's first. -4 plus 0, that's -4. -4 plus 1, that's -3. -4 plus 4, that's 0. -4 plus 9, that's 5. So personally, when I do transformations, I do all my x's, unless there's nothing to do. Oftentimes there's nothing to do over here, but if there is, do it first, and then do the y's last. Now, I'll leave it to you to do it in any order you like. So that's going to stay 0. That one's going to be -1/2. That one's going to be -1. And that one's going to be -3/2. All right, and remember our vocabulary. This is called our terminal point. So make sure we plot that point first. Okay, so let's see. This one's a little hard to see. So we sometimes do this. You might notice this on the computer occasionally. We'll skip every other square so that it blows up the graph a little bit. It makes it easier to see. So this is a doubled scale here. So that's 1, that's 2, that's -1, and that's -2. And -3, and so on and so forth. Okay. All right, so what do we got? We're going to plot this point first, -4 and 0. That is our terminal point. That means that the graph does not go past that point. All right. That's either the starting point or the ending point, depending on how you're looking at your life. Now, again, on the computer, you can just pick. On the computer, I probably would just do these two. So on the computer, I would just do 0, -1, and boom, I'd be done. The problem is, if you're not using a computer, you will inevitably draw a straight line. Yeah? And back in the classroom, which I hope someday we can go back to school, I will hand you out a piece of graph paper and I'll ask you to draw it with your pen or your pencil. And inevitably, if you only do 2 points, you'll draw a straight line. So I'm going to go ahead and do all of them. -3 and -1/2. So that's right about there. Yeah, 1/2 is halfway between 0 and -1. The computer will occasionally let you draw halves. I mean, play around with the mouse. If it lets you plot a half, then you certainly can. 5 and -3/2. Uh-oh. 4, 5 is way over here. Now be careful. -3/2 is not anywhere near -3. It's actually 1.5. So be careful. This is -1.5, not -3. I've seen people go da 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 da, and then all of a sudden they've got a point way down here, completely off base, right? So this is your graph. It's slightly bendy to get back to its terminal point. And there you go. That's your graph. Now the graph does continue forever. You might not see the arrow. Oftentimes the computer doesn't show the arrow. The arrow is away from the terminal point. All right, so you'll never, ever, ever go past the terminal point. This is not a free answer for domain and range. You're going to have to work a little bit to get the answer. So the domain starts at -4. It's including -4. And it goes all the way to positive infinity. The range is the y values, the up and down. So this arrow is going down to -infinity. Yeah, that's -infinity down here. That's where this is heading. Right? It's getting closer and closer and closer to -infinity. And then look at the y value at the terminal point. The y value is not -4. The y value is 0. So the range is from -infinity all the way to 0. That's the range. This is the domain. So domain is x, range is y. These are kind of fun, huh? I don't know. I mean, I tell you what, there could be worse things to do. So sometimes when I think about, I mean, I like math, but, math is a little bit of a love-hate relationship. You love it, but then you get really, stuck. I know students get frustrated and they start to hate it. But I always just imagine there could be much worse things to do. Think of all the things that could be worse than this. Let's do another one. Okay, let's do another one. This one's called G. It really doesn't matter. I'm just trying to get some variety in the diet. I want to make something very clear about cube roots. Sometimes these numbers are difficult to tell apart. The big number is called the scalar. And that's going to tell us that it's going to have a stretch. Okay. The little number here is called the index. All it does is it tells us that it's a cube root. That's all the index does. It indicates. That's what an index does. It indicates what you are dealing with, who your parent function is. Okay. So let's go ahead and do it. Who is the parent? Or the mother function? I just said it. Cube root, yeah? Are there any reflections? Yes. All right. Where is the reflection? Right here. It's on the inside. If it's on the inside, you're going to reflect over or across the y-axis because it's on the inside. Are you going to stretch or compress? Yes. Vertically, I already said that. Stretch vertically by a factor of 4. So the graph's going to get 4 times taller than it originally was. Are you going to do a horizontal shift? No. Yeah. There are no additions or subtractions inside of the radical symbol. There is a -1, but that's a reflector. Yeah. That's not a shifter. Is there a vertical shift? Yes. Which way? Up 2 units. Okay. I guess we should go ahead and graph this thing. Go ahead and graph it. I know, whenever I answer all these questions, I think this will be the last time I do all these questions here. Although I'm still going to say it. I'm still going to think it. I'm just maybe not going to write it every single time. All right, so let's going to go ahead and go back and do our work now. So we take our mother function or our parent function. I hope you've noticed that the cube root is just the reverse values of x and y as the cubic. So if you memorize the cubic, which we just did a few minutes ago, the cube root, you just reverse the x's and y's. You can kind of tell by the way the shape goes, right? All right, so the 4, that's a scalar. We're going to multiply all of the y values by 4. The -1, we're going to multiply all the x values by -1. Make sure you use parentheses, otherwise you might subtract 1 instead. And then the +2, that's the last thing. You're going to add 2. Always do your shifting last. Either shift it up, or shift it down, or shift it left, or shift it right, or whatever. Send it through the transform. Give it a name. G of x, that's your parent, gave you that name. Sounds pretty familiar, right? Do all your x's first. Negative times a negative is a positive. Negative times a negative is a positive. Negative times 0 is 0. Negative times a positive is a negative. Negative times a positive is a negative. So I have negative, negative, positive, negative, negative, positive. Negative 0 is 0. Negative, positive, negative, negative, positive, negative. Just check your signs. I already know. If you're going to make a mistake, that's where it will be. It will be some very basic plus or minus mistake. Now let's come over here, multiply by 4, and then add 2. Negative 2 times 4 is negative 8. Negative 8 plus 2 is negative 6. You could do all this with mental math. If you want to have your calculator handy or some scratch paper, it's not a bad idea. Negative 1 times 4 is negative 4. Plus 2 is negative 2. 0 times 4 is 0. Plus 2 is 2. 1 times 4 is 4. Plus 2 is 6. 2 times 4 is 8. Plus 2 is 10. Keep your eye on the ball. The 0, 0. That's the inflection point. Make sure you plot that point first. While you're finishing up your notes, I will get my board ready to go. I'm assuming you're taking notes. Some of these points may not fit on my graph board here. I don't have guarantee. I really only need 2 of them to fit, but it'd probably be better to get 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. I always look at the values before I make my graph, because I know I can get them all on there. 1, 2, 3, 4, 5, 6. So that one's barely going to fit. I really don't need that arrow right there. It's kind of getting in the way. So this is my my G, also known as Y, and this is my X. I don't think this one's going to fit. Yeah, look, 1, 2, 3, 4, 5, 6. Yeah, so the 10 is not going to fit. I'm not going to do it. All right, so 0, 2, that's right here. 0, 2. I typically don't mark the 0, but 0 is technically right there, right? The origin. I think it's so obvious that that's 0, I don't usually mark it. I only mark the values that I really want to make sure I can keep my eye on. Negative 1 and 6. So negative 1 is here, and then 2, 3, 4, 5, 6. So right about there. Negative 1 and 6. 1 and negative 2. So there's 1, and then there's negative 2 on the y-axis. This is negative 1 on the x-axis. So this is 1, and this is negative 2. There we go. That's probably enough, but why don't I just do one more? 8 and negative 6, so there's 8, there's negative 6, so way down here. And there you go. And you can kind of see where this point would be, because look, here's negative 8. So if my board were bigger, it would go off the board and it would be up here. You know, if my board were a little bit bigger, I could go all the way to 10. I'm not really going to do that, but at least you can kind of see that the shape makes sense. All right. And again, you get a couple free answers here. This is a cube root, so you might as well take your free answers, domain and range. Yeah. I love to give away those free answers. I've had students open up a problem on a quiz or a test, and they can remember the free answers. They grab them and they get them. And that way, if you screw up on solving or graphing or any of the other technical details, at least you're getting your free points. I want to make one thing clear. all points are points. So a free point that you got for absolutely nothing is worth the same amount as a point that you worked your butt off for. A point that you spent all this energy trying to get. It's the same value. It's a point. Right? I don't discriminate between the different types of points. Points are points. I think I have time for one more. And I have to end this and go and make a part 3, it looks like. Maybe. I don't know. We'll see. Don't quote me on that, but I'm definitely going to end this after one more example. I don't know. Can you guys hear that? I have some work done. So construction in the garage. All right, last example. Example 8. All right, so who is the mother function? The mother is reciprocal. Y equals 1 over x. If you see a negative out in front, that means the same thing as -1. So this literally means -1. All right, so I usually combine the negative and the 1 and just write it as -1. Okay, that is a reflection. And that reflects about the x-axis. All right. And then we're going to shift left. I'm just going to write it here. 6 units and up 3 units. So we take our mother table. Now remember, I don't know if you remember, it's been a long time since we did this one. This one has a pretty big mother function table. Okay, it's got a big one, yeah? So it's -2, -1, -0.5, 0, 0.5, 1, and 2. This is the biggest mother function table that we have. Now, I love the name of this function, reciprocal, because it tells me very easily how to fill out the form. All of the y values are the reciprocal of the x values. So the reciprocal of -2 is -0.5. The reciprocal of -1 is still -1. The reciprocal of -0.5 is -2. The reciprocal of 0 does not exist. Ah, that is an asymptote. It's actually 2 asymptotes. Yeah? And I'll tell you how to get to them in a minute. I'm going to leave DNE there to remind me that's what the dotted line means. Dotted line, DNE. Yeah, it does not exist. That's why it's a dotted line. Finish filling out the table. The reciprocal of 0.5 is 2. Reciprocal of 1 is 1. The reciprocal of 2 is 0.5. Okay. So we're going to do our reflections first. Multiply everybody by -1. I even do the DNE. Yeah. I mean, it's not going to change anything. I just like everybody to get it. Yeah. Then you're going to go left 6. I even do the DNE row. All right. Again, I know I'm going to say this a lot, and if I do end up doing a part 3, which it kind of looks like it because I'm getting really low on time here, do not subtract 6, add -6. All right, unless you want to get it wrong. I mean, technically subtracting 6 and adding a -6 should give you the right answer. It's just the way the human brain works. It typically doesn't. It gives you the wrong answer. So if you want to do it correctly, add -6. And then finally, up 3, go over here and add 3 to all of the y values. Okay, so we're going to send it through our transformation, undergoing the transformation, give it a name. This name is F. I like to give it its name after it's, come out of the transformation. So you have now been transformed, and your name is now f of x. This is a lot of arithmetic here, so let's just do it all together here. Negative plus a negative is a -8. Yeah, I'm adding 2 negatives. That's why I don't want you to subtract. Because typically when you subtract negatives, you end up going the wrong way. I mean, unless you're an expert. And if you're an expert, you can do it any way you like. That's the benefit of being an expert. Yeah. If you're still learning, then do it my way. -6 and -1, that's -7. -6.5. I know I avoid decimals, but this is an exception. Yeah. When I'm dealing with halves, I like to just use 0.5. It's so much easier to write. -6 plus 0. I'm going to call that -6, and I'm actually going to write it in red because that's going to be my asymptote. All right. DNE times -1, it's still DNE, and then plus 3. So that would be plus 3. Okay. Now make sure that you realize that this is your DNE row. That's why I wrote them in red. These points do not actually exist. All right. The DNE actually applies to this whole row here. It's kind of like the vertex or the inflection point. It kind of has that same flavor. When you're solving when you're evaluating all these tables. But when you go to graph, you'll see what I do differently. All right, we're almost done filling out the table, and then we have to draw this mother function. -6 plus a half is -5.5. -6 plus 1 is -5. And -6 plus 2 is -4. And now I got to do the y values. Whew. Negative times a negative is a positive a half plus 3. That's 3.5. -1 and -1 is +1 plus 3 is 4. -2 and -1 is 2. 2 plus 3 is 5. Okay. DNE, we've already done that. 2 times -1 is -2, plus 3 is 1. -1 times +1 is -1, plus 3 is 2. And then -1 times a half is -1/2, plus 3 is 2.5. If you have to use your calculator or your cell phone or something like that, you certainly can. All right, it's a college math class. Use arithmetic until your brain starts to hurt or until you start making lots of mistakes, and then use your calculator as an insurance. Yeah. Okay, this will be our last graph for this lesson. Let's see. I'm putting my y-axis way over here because notice that all of my x's are negative, so the whole graph is going to live way over here. So this whole side will be blank. I probably could have scooted it over more, but I'm not going to. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Good, I fit it. -8, nice. I was trying to fit it all on there. I really want to exaggerate my scale because I have decimals here. All right, 1, 2. Sorry about that. I changed my mind on where I want to put my x. So that's 1, that's 2, that's 3, that's 4. I still don't like that. This is one thing you won't have to worry about because your graphing plane is all set for you. 1, 2, 3, 4, 5. You see why I'm doing that? I want to make sure that I can get all the way to 5. I don't normally do this, but I'm going to this time. All right. And then -1, -2, -3. I'm trying to get all the way to -8. -4, -5, -6. 7 negative and 8 negative. Okay. Now here's the deal. You wonder why I'm making such a big deal about this? Because when you graph it, you have to plot the DNE first. These are your asymptotes. So you're going to click at -6 and 3. You're going to click right here, and then it will automatically fill it in if you're using the right button on your graphing board there. Don't worry, it'll be pretty obvious. It'll look just like this. If it doesn't look like this, then you're using the wrong tool. There's a little list of tools underneath the graphing board. Okay, you want to pick the one that looks like 2 dotted lines with a curve. All right, now if you're doing your homework, you can just pick one other point, say -5 and 2, and the computer will automatically finish the graph for you. So it'll sort of look like this. And you're done. Yeah. So this is how it would look on the homework. It's just 2 dots. 1 dot for the asymptotes and then another convenient point. I picked that one because it doesn't have any decimals. All right? You could have also picked this one here. -7 and 4. And there you go. You do not have to plot the decimals. All right. Unless you want to. You certainly can. Watch. -8 and 3.5. That's right about here. Oh, there it is. -6.5 and 5. Hey, that's right there. So even if you don't plot the decimals, they're there. Yeah. -5.5 and 1. That's right there. Yeah. Oh no, it's actually right there. Actually, look where 1 is. I almost screwed that one up. -4 and 2.5. That's right there. Now this 2.5. Halfway between 2 and there's 3. And so this is your transformed function. I might ask you for the domain and range. The domain is all of the x values except the DNE. All right, the DNE means it does not exist. So 6, negative, union, 6, negative 6 to infinity. Does not exist means open. It means you're not actually touching negative 6 because you can't touch something that does not exist. Right? You can't put a dot at a point that doesn't exist. In the range, same thing, just look at the y value and make that does not exist. So the same idea. Yeah. Okay, I wish I could say we were done with 3.5. I'm going to go to my office hours now on Zoom, so if you have any questions, I don't know when you're going to watch this, but I mean, you might be watching this, and it's not my office hours right now, but in real time, it's almost my office hours. So maybe I'll see you on the internet.